the invisible foundations of reality. The universe around us is far more vast and mysterious than what our eyes can show us. But don't worry, we'll take this journey slowly, calmly, discovering each piece at a gentle pace. When you look up at the night sky, you're seeing only a tiny fraction of what's really there. Your eyes are remarkable organs, but they can only detect a narrow band of light, a small window into the cosmos. This isn't a limitation to feel frustrated about. Instead, it's an invitation to understand how much more exists beyond our direct perception. Light comes in many forms. The light you see, the visible spectrum, represents just 1% of all the electromagnetic radiation flowing through space. Imagine standing by a vast ocean and only being able to see the waves at the surface. The depths below remain hidden, yet they contain most of the water. This is how our relationship with the universe works. We see the surface, while countless phenomena occur in ranges our eyes simply weren't designed to detect. Let's start with something close to home, something familiar. The sun provides warmth and light every day. When you feel sunshine on your skin, you're experiencing visible light and infrared radiation. But the sun emits so much more. It constantly releases radio waves, ultraviolet light, X-rays, and even gamma rays. Each type of radiation tells a different story about what's happening in our star. Each one carries information that visible light alone cannot convey. Your body responds to some of these invisible forms of light. When you feel warmth from the sun, that's infrared radiation at work. Your skin cannot see infrared light, but it can feel it as heat. This is one of the gentlest reminders that reality extends beyond sight. The warmth you feel on a sunny day is electromagnetic radiation, just like visible light, simply vibrating at a different frequency. Scientists discovered these invisible forms of light gradually, over centuries. In the early 1800s, William Herschel, a musician who became an astronomer, placed thermometers in different colors of sunlight split by a prism. He noticed something curious and unexpected. The thermometer placed just beyond the red portion of the spectrum, where no visible light appeared, showed the highest temperature. He had discovered infrared radiation, light that exists just below the frequency our eyes can detect. Shortly after, Johann Ritter found something on the other end of the spectrum. He used silver chloride, a chemical that darkens when exposed to light. When he placed it beyond the violet end of the visible spectrum, the chemical still darkened, even though no visible light reached it. He had discovered ultraviolet radiation, light vibrating at frequencies just above what human eyes can perceive. These discoveries opened entirely new ways of seeing the universe. They revealed that human vision, while useful for navigating daily life, shows only a thin slice of reality. This isn't something to feel sad about. Instead, it's something to feel curious about. Every limitation in our perception has led to new tools, new instruments, new ways of extending our awareness into realms we cannot naturally access. Radio waves exist at the low-frequency end of the electromagnetic spectrum. These waves are huge, sometimes measuring meters or even kilometers from peak to peak. When you listen to music on a radio, your device is detecting electromagnetic radiation that passes right through walls, through your body, through nearly everything around you. You cannot see these waves, but they carry information across vast distances. The universe produces radio waves naturally. Pulsars, which are rapidly spinning neutron stars, emit beams of radio waves like cosmic lighthouses. Galaxies generate radio emissions from the movements of charged particles in their magnetic fields. Even the gas between stars produces faint radio signals. For decades, astronomers have been listening to these cosmic radio waves, mapping structures in the universe that remain completely invisible to optical telescopes. Imagine standing in a room where music is playing, but your ears don't work. You might see people moving their bodies in rhythm, and from their movements you could deduce that sound exists. This is similar to how we discovered many invisible phenomena. We noticed effects, patterns, behaviors in the universe that didn't make sense based only on what we could see. Those observations led us to realize that much more was happening than our eyes revealed. Microwaves sit between radio waves and infrared in the electromagnetic spectrum. Your microwave oven uses these waves to heat food. The waves cause water molecules to vibrate rapidly, generating heat through friction. The universe also contains a sea of microwaves, a faint glow that fills all of space. This microwave background radiation is ancient light, stretched by the expansion of the universe over billions of years. We'll explore this cosmic microwave background more deeply in a moment, but for now just let yourself absorb this idea. Space itself glows with invisible light, a whisper from the earliest moments of time. Moving up in frequency, we encounter infrared radiation. This is the warmth you feel from a fire, from another person's body, from any object warmer than its surroundings. Infrared telescopes can see through dust clouds that block visible light. Star nurseries, where new stars are forming inside dense clouds of gas and dust, appear dark to optical telescopes. But in infrared, they glow brightly, revealing the warm processes of stellar birth hidden within. The visible spectrum sits in the middle of this electromagnetic range: red, orange, yellow, green, blue, indigo, violet. These are the colors human eyes evolved to detect. This narrow band happens to be where the sun emits most of its energy, which makes sense. Life on Earth evolved under sunlight, so our eyes naturally adapted to detect the wavelengths that were most abundant and useful for survival. But the universe doesn't care about human convenience. Most of the cosmos operates in wavelengths we cannot see. Understanding this helps us appreciate both the power of human ingenuity in building instruments to extend our senses and the humility required to acknowledge how limited our natural perception truly is. Beyond violet lies ultraviolet radiation. The sun emits significant ultraviolet light, though most of it is absorbed by Earth's ozone layer before reaching the surface. This is fortunate, because ultraviolet radiation carries enough energy to damage living cells. Sunburn is the result of ultraviolet radiation causing injury to skin cells. Yet this same radiation allows us to see aspects of the universe invisible in ordinary light. Hot stars emit most of their light in ultraviolet wavelengths. Ultraviolet telescopes in space reveal the hottest, most energetic objects and events in the cosmos. X-rays carry even more energy than ultraviolet light. Medical X-ray machines use this property to create images of bones inside the body. X-rays pass through soft tissue, but are blocked by denser materials like bone. In space, X-rays are produced by some of the most violent processes imaginable. Black holes, as they consume matter, heat the surrounding material to millions of degrees. This superheated matter emits X-rays, supernova explosions, where massive stars destroy themselves, produce floods of X-ray radiation. Observing the universe in X-rays reveals catastrophic events and extreme conditions that visible light alone would never show. At the highest energies come gamma rays. These are the most energetic form of light, carrying tremendous amounts of energy in each photon. Gamma rays are produced in nuclear reactions, in particle collisions at near light speed, and in the most extreme cosmic events. When massive stars collapse, they sometimes produce focused beams of gamma rays so intense they can be detected from billions of light years away. These gamma ray bursts represent the most powerful explosions in the universe since the Big Bang itself. All of these forms of light, from low-energy radio waves to high-energy gamma rays, travel at the same speed through empty space. The speed of light, approximately 300,000 kilometers per second, represents the universe's speed limit. Nothing can travel faster. This speed connects space and time in profound ways that we'll explore gently as we continue. Now, let's think about what this means for understanding the universe. Imagine trying to understand a symphony by only hearing the violin section. You'd miss the cellos, the brass, the percussion, the woodwinds. Each instrument contributes something essential to the complete experience. Similarly, observing the universe in only visible light means missing most of the story. Modern astronomy uses instruments that detect all these wavelengths, building up a complete picture from radio to gamma rays. Consider a galaxy. In visible light, you see its stars, the accumulated glow of billions of suns. In infrared, you see dust lanes and star-forming regions. In X-rays, you see the supermassive black hole at its center and remnants of supernova explosions. In radio waves, you see the structure of its magnetic fields and the jets of material shooting out from its core. Each wavelength reveals something the others miss. Together, they tell the complete story of what that galaxy truly is. This principle applies to everything in the universe. The sun, which appears as a bright yellow disk in visible light, looks completely different in ultraviolet, showing the churning convection of its surface and the explosive events in its atmosphere. In X-rays, the sun reveals its corona, the million-degree outer atmosphere that defies easy explanation. Each view complements the others, building understanding layer by layer. Take a moment to appreciate this. The universe is more than we can see, much more. And humanity has developed the tools and knowledge to perceive these hidden layers. We've extended our senses far beyond what evolution provided, creating instruments that can detect the faintest radio whisper from a galaxy billions of light years away, or the gamma-ray flash from a collapsing star halfway across the observable universe. But electromagnetic radiation isn't the only thing we cannot see. The universe contains other invisible phenomena, things that don't emit light at all, yet shape everything around them. Let's explore these mysteries slowly and carefully. Gravity is invisible. You cannot see it, touch it, or directly detect it with any human sense. Yet gravity governs the motion of every object in the universe. It keeps your feet on the ground, holds the moon in orbit around Earth, binds the solar system together, and organizes galaxies into vast clusters. Gravity is a fundamental force, woven into the fabric of space-time itself. Albert Einstein revolutionized our understanding of gravity in the early 20th century. His general theory of relativity describes gravity not as a force in the traditional sense, but as a curvature of space-time. Massive objects bend the space and time around them. Other objects move through this curved space-time, following paths we perceive as orbits or falling. Imagine placing a heavy ball on a stretched rubber sheet. The ball creates a depression, and if you roll a smaller ball nearby, it will spiral around the depression rather than traveling in a straight line. This is a simplified way to visualize how mass curves space-time. The Earth creates a depression in space-time, and the Moon moves through that curved space, creating its orbit. You cannot see this curvature directly. Space-time is not something you can look at, but you experience its effects constantly. When you drop something, it falls because it's following the curve in space-time created by Earth's mass. When you feel the pull of gravity, you're experiencing geometry itself. Gravity waves, ripples in space-time caused by accelerating massive objects, were predicted by Einstein but not detected until 2015. These waves travel at the speed of light, stretching and squeezing space itself as they pass. When two black holes spiral together and merge, they produce gravity waves powerful enough to detect on Earth, even though the event might occur 1 billion light-years away. The detectors that found these waves, called LIGO, use lasers to measure changes in distance smaller than the width of a proton. The waves from colliding black holes change the length of 4-kilometer-long detectors by an almost inconceivably small amount. Yet it was enough to confirm Einstein's century-old prediction. Humanity detected ripples in the fabric of space-time itself, something completely invisible, something that is not light or matter or energy in the ordinary sense, but the geometry of reality, flexing and flowing. This is remarkable when you pause to think about it. We've learned to perceive things that have no business being perceptible. Gravity waves don't interact with matter in the way light does. They simply stretch and compress space as they pass. Yet through careful engineering and deep understanding of physics, we made them detectable. Now consider dark matter. This is one of the most profound mysteries in modern science. When astronomers measure the motion of galaxies, they find something unexpected. Stars in the outer regions of galaxies orbit far too quickly. Based on the visible matter in these galaxies, the outer stars should move much more slowly, or they should be flung out into space entirely. Yet they orbit at high speeds, held in place by more gravity than the visible matter can provide. This pattern appears everywhere astronomers look. Galaxy clusters contain more gravity than their visible matter can explain. The way galaxies move, the way light bends around massive objects, the structure of the cosmic web, all of it requires more mass than we can see. Much more. Calculations suggest that roughly 85% of the matter in the universe is dark matter, invisible to all forms of electromagnetic radiation. Dark matter doesn't emit light. It doesn't absorb light. It doesn't reflect light. It doesn't interact with electromagnetic radiation at all, as far as we can tell. Yet it must exist, because we see its gravitational effects everywhere. Galaxies are embedded in vast halos of dark matter. These halos extend far beyond the visible portions of galaxies, providing the gravity necessary to hold everything together. Nobody knows what dark matter is made of. It's not ordinary matter, not atoms and molecules like everything you've ever touched. It must be some form of particle that only interacts through gravity, passing through ordinary matter like a ghost. Enormous efforts are underway to detect dark matter particles directly, to understand their properties, to figure out what comprises most of the matter in the universe. Think about that for a moment. Everything you've ever seen, every star, every planet, every galaxy, every nebula, all the ordinary matter in the entire observable universe represents only 15% of the total matter. The rest is invisible, detectable only through its gravitational influence. The universe is mostly made of something we've never seen, never touched, never directly detected. This should inspire wonder, not fear. The universe is deeper and stranger than we imagined. Our eyes show us a beautiful cosmos filled with light and structure, but they show us only a fraction of what exists. Most of reality operates beyond human sight, in invisible wavelengths, in particles that don't interact with light, in geometric ripples of space-time itself. And there's more. Dark energy represents perhaps the most mysterious component of the universe. In the late 1990s, astronomers studying distant supernovae made a shocking discovery. The expansion of the universe is accelerating. Not only is space expanding, carrying galaxies apart, but the rate of expansion is increasing over time. This shouldn't happen. Gravity should slow the expansion. The mutual gravitational attraction of all the matter in the universe should gradually break the expansion, perhaps even reversing it eventually. Instead, something is pushing space apart, overcoming gravity, making the expansion faster and faster. Scientists call this mysterious influence dark energy. It makes up roughly 68% of the total energy content of the universe. We don't know what it is. We don't know how it works. We can only observe its effect, the accelerating expansion of space itself. Dark energy doesn't emit light. It's not made of particles in the ordinary sense. It seems to be a property of space itself, a form of energy intrinsic to the vacuum. The more space there is, the more dark energy there is. As the universe expands, more space comes into existence, bringing more dark energy with it, which causes even faster expansion. This creates a feedback loop that will ultimately determine the fate of the cosmos. Let's pause and take stock. When you look at the night sky, you see stars and galaxies, beautiful points of light scattered across darkness. What you're seeing is extraordinary, but what you're not seeing is even more remarkable. You're not seeing the dark matter that provides most of the gravity holding those galaxies together. You're not seeing the dark energy causing space itself to expand at an accelerating rate. You're not seeing the infrared, ultraviolet, X-ray, radio and gamma-ray emissions telling crucial parts of each object's story. You're not seeing the gravitational waves rippling through spacetime as massive objects accelerate and collide. The universe beyond human sight is not separate from the universe we see. It's the same universe, the same reality, simply operating in wavelengths and forms our eyes weren't designed to detect. Through instruments and mathematics, through careful observation and creative thinking, humanity has learned to perceive these hidden aspects of existence. This journey of discovery continues. Every answer raises new questions. Every mystery solved reveals deeper mysteries. The universe doesn't make itself easy to understand, but it also doesn't hide. Everything operates according to natural laws, producing effects we can measure and study. The invisible becomes visible through human ingenuity and curiosity. Consider neutrinos, tiny particles with almost no mass that pass through matter as if it weren't there. Billions of neutrinos from the sun pass through your body every second. They come from nuclear reactions in the sun's core, traveling at nearly the speed of light, passing through the entire Earth without slowing down or stopping. You cannot feel them. They don't affect you in any noticeable way, yet they're there, a constant invisible rain of particles from our star. Neutrinos carry information about processes we cannot observe any other way. The core of the sun is opaque. Light generated there takes hundreds of thousands of years to random walk its way to the surface, but neutrinos escape immediately, traveling straight out without interaction. By detecting neutrinos, we can observe nuclear reactions happening right now in the sun's core, something impossible with light alone. When a massive star explodes as a supernova, most of the energy is carried away by neutrinos, not light. In 1987, when a star exploded in a nearby galaxy, detectors on Earth caught a brief burst of neutrinos passing through the planet. These particles traveled 160,000 light-years from the supernova to Earth, arriving hours before the light did, because they escaped the exploding star earlier. This was the first time humanity detected neutrinos from beyond our solar system, opening another invisible window onto the cosmos. The universe operates on scales both larger and smaller than human comprehension easily grasps. The smallest scales are quantum mechanical, where particles behave in ways that defy everyday intuition. The largest scales involve billions of light years, structures so vast that light needs billions of years to cross them. Human sight evolved to handle scales from millimeters to kilometers, the range useful for survival. Everything beyond that in both directions required tools to detect and understand. Quantum mechanics describes reality at the smallest scales. At this level, particles don't have definite positions until measured. They exist in superpositions, being in multiple states simultaneously, until observation forces them into one state. This isn't because our measurement tools are crude. It's the fundamental nature of reality at quantum scales. Particles are both waves and particles, exhibiting properties of each depending on how you observe them. You cannot see quantum superposition. It occurs at scales far too small for human eyes. Yet it's absolutely real, confirmed by countless experiments over the past century. Your computer, your phone, modern technology in general relies on quantum mechanics being correct. The electrons in the circuits are quantum objects behaving according to quantum rules. The invisible quantum world makes the visible technological world possible. At the largest scales, the universe exhibits structure invisible from any single vantage point. Galaxies cluster together in groups and clusters. These clusters connect through filaments of galaxies, forming a cosmic web that spans the observable universe. Between the filaments lie vast voids, regions with very few galaxies. This structure, called the cosmic web, is too large to see from Earth. We discovered it by painstakingly mapping the positions and distances of millions of galaxies, building up a three-dimensional picture of the large-scale universe. The cosmic web formed through the influence of dark matter. In the early universe, tiny fluctuations in density allowed some regions to have slightly more matter than others. Gravity amplified these differences. Regions with more matter attracted even more matter, while regions with less matter lost their material to the denser areas. Over billions of years, this process created the filaments, clusters, and voids we observe today. You cannot step back and see the cosmic web with your eyes. It's too vast. But through decades of surveys and observations, astronomers have mapped it in incredible detail. This invisible structure, shaped by invisible dark matter, organized the visible universe into the forms we observe today. Now let's talk about something even more invisible, something that doesn't exist in space at all. Time itself is invisible. You cannot see time. You cannot touch it. You experience its passage subjectively, but time itself remains intangible. Yet time is as fundamental to reality as space. In fact, they're connected into a single unified framework called spacetime. Einstein's theory of relativity revealed that time is not absolute. It flows at different rates depending on motion and gravity. Time passes more slowly in strong gravitational fields. Time passes more slowly for objects moving at high speed. These effects are tiny in everyday life, but they're measurable and real. Satellites in orbit experience time slightly differently than clocks on Earth's surface. GPS systems must account for these relativistic time differences to provide accurate positions. At the event horizon of a black hole, time dilation becomes extreme. From the perspective of a distant observer, time appears to stop for anything falling toward the event horizon. The falling object appears to freeze, taking infinite time to cross that boundary. Yet from the perspective of the falling object, nothing special happens at the event horizon. It falls through in finite time, experiencing nothing unusual at that particular point. This is profoundly strange. Time is not the steady, universal flow it appears to be. It's flexible, variable, dependent on conditions. Yet you cannot see this. You cannot directly perceive time dilation or the warping of time by gravity. You can only measure it with precise instruments and careful experiments. The universe contains many invisible boundaries and horizons. The event horizon of a black hole is invisible. It's not a physical surface. It's simply the location where escape velocity equals the speed of light. Inside the event horizon, all paths lead toward the singularity. Outside, escape is possible. The horizon itself is just a geometric boundary in curved spacetime, marking a point of no return. The observable universe has a horizon too. Light from beyond this horizon hasn't had time to reach us yet. The universe is 13.8 billion years old, but due to expansion, the observable universe extends about 46 billion light-years in every direction. Beyond that lies more universe, potentially infinite, but we cannot see it. Light from those regions hasn't had time to traverse the expanding space between there and here. This cosmic horizon is invisible, not because nothing exists beyond it, but because the information hasn't reached us yet. As time passes, the horizon expands as light from more distant regions arrives. However, due to the accelerating expansion driven by dark energy, there are regions of space currently visible that will eventually disappear beyond our horizon. The expansion will carry them away faster than light can travel through the expanding space between us, making them forever unreachable and eventually unobservable. The concept of an invisible horizon, a boundary beyond which observation becomes impossible, appears throughout physics. It's a reminder that human perception and even human measurement have fundamental limits. Some things cannot be observed, not because of technological limitations, but because of the basic structure of spacetime and the laws of physics. Magnetic fields are invisible to human eyes, yet they permeate space. Earth has a magnetic field generated by currents in its molten iron core. This field extends far into space, creating the magnetosphere that protects us from harmful solar radiation. You cannot see the magnetosphere, but you can see its effects. The aurora, those beautiful curtains of light in polar skies, result from charged particles from the sun spiraling along Earth's magnetic field lines and colliding with molecules in the upper atmosphere. The sun has an incredibly complex magnetic field that drives solar activity. Sunspots are regions of intense magnetic field breaking through the visible surface. Solar flares and coronal mass ejections are magnetic phenomena, explosive releases of energy when twisted magnetic field lines reconnect. These events can send billions of tons of charged particles streaming toward Earth, potentially disrupting satellites and power grids. All of this is driven by invisible magnetic fields we can only detect indirectly. Galaxies have magnetic fields too, stretching across thousands of light years. These fields influence the motion of charged particles and play a role in star formation. They're detected through their effects on radio waves and polarized light, but the fields themselves remain invisible. The universe is filled with phenomena we cannot directly perceive. Cosmic rays, high-energy particles accelerated to near light speed by supernova shocks and other violent processes, constantly bombard Earth. Most are deflected by our magnetic field or collide with atoms in the atmosphere. You cannot see them or feel them, but they're there. Some carrying more energy in a single particle than a thrown baseball contains. The vacuum of space itself is not truly empty. Quantum mechanics tells us that even empty space contains a seething foam of virtual particles, constantly popping into and out of existence. These quantum fluctuations are real and measurable. They affect the behavior of particles and fields. The vacuum has energy, vacuum energy, which may be connected to dark energy. Even nothing, it turns out, is something. All of this exists beyond human sight. All of this is real. The universe reveals itself not just through what we can see, but through careful measurement, creative thinking, and building instruments that extend our senses into realms evolution never prepared us for. As we near the end of this first chapter, take a moment to reflect. The universe you perceive with your eyes is beautiful and worthy of contemplation, but it represents only a tiny fraction of reality. Most of the universe operates in wavelengths invisible to you. Most of the matter is dark matter you cannot detect. Most of the energy is dark energy you don't understand. Time flows variably. Space curves under mass. Particles exist in superposition, and fields permeate everything. None of this makes the visible universe less real or less important. Your eyes show you stars and planets, mountains and oceans, other people's faces. This is the reality you interact with daily. But knowing that more exists that the invisible universe surrounds and interpenetrates the visible one, deepens appreciation for how strange and wonderful existence truly is. We've built tools to see the unseeable. Radio telescopes detect whispers from distant galaxies. X-ray satellites observe black holes feeding on nearby stars. Gravitational wave detectors feel space-time itself ripple. Particle accelerators probe the quantum realm. Each instrument extends human perception a little further, revealing layers of reality previously hidden. And the exploration continues. New instruments come online. New observations are made. New mysteries appear. The universe doesn't run out of secrets. Each discovery opens new questions. Each answer reveals how much remains unknown. But this is not frustrating. It's exhilarating. It means there's always more to learn, always deeper understanding to pursue. The universe beyond human sight is not closed to us. It's simply invisible to our limited biological senses. Through science and technology, through patience and curiosity, we make the invisible visible, the unknown known. In the next chapter, we'll explore how we came to understand these invisible aspects of the cosmos. We'll trace the history of discovery, the brilliant insights and patient observations that revealed layer after layer of reality. We'll see how each breakthrough built on previous knowledge, how humanity gradually extended its perception from the visible surface into the hidden depths of existence. For now, rest with this knowledge. You live in a universe far stranger and more beautiful than your eyes alone can show you. The visible cosmos represents just the beginning. Beyond sight lies most of reality, operating according to natural laws we've learned to decode. You may not see it, but it's there, always there, invisible but knowable, hidden but discoverable. Take your time with these ideas. Let them settle. The universe has existed for nearly 14 billion years. It will continue for trillions more. There's no rush. Understanding can develop slowly, peacefully, like dawn light, gradually revealing a landscape that was always there, just waiting for illumination. Mapping the invisible cosmos. The story of how we came to perceive the invisible universe unfolds across centuries, a gradual awakening to layers of reality our eyes alone could never reveal. Each discovery built upon the last, each insight opening new questions, new mysteries to explore. This journey of understanding required patience, careful observation, and willingness to accept that the cosmos might be far stranger than it appears. For thousands of years, humanity observed the heavens with nothing but naked eyes. Ancient astronomers tracked the sun's path across the sky, noted the phases of the moon, followed the wandering planets among the fixed stars. They were remarkably skilled, predicting eclipses and measuring the precession of Earth's axis over long periods. Yet they could only work with what their eyes could detect, that narrow band of visible light we discussed earlier. The invention of the telescope in the early 1600s marked humanity's first step beyond biological vision. When Galileo pointed his small telescope at the night sky, he saw mountains on the moon, moons orbiting Jupiter, and countless stars previously invisible. The universe immediately revealed more complexity, more depth than anyone had imagined. Over the following centuries, telescopes grew larger and more sophisticated, gathering more light, revealing fainter and more distant objects. But these instruments still operated within the visible spectrum, extending the reach of human vision without fundamentally changing what kind of light we could perceive. The true breakthrough came from studying sunlight itself. When white light passes through a prism, it separates into a rainbow of colors. In the early 1800s, William Herschel placed thermometers in different parts of this spectrum, measuring the temperature of each color. He noticed something unexpected. Beyond the red end of the spectrum, where no visible light appeared, his thermometer registered the highest temperature. Heat existed beyond what eyes could see. Herschel had discovered infrared radiation, light that vibrates at frequencies just below what human vision can detect. Soon after, Johann Ritter found ultraviolet radiation beyond the violet end of the spectrum. He used silver chloride, a chemical that darkens when exposed to light. Even in regions where no visible light fell, the chemical still reacted. The electromagnetic spectrum extended beyond human perception in both directions. This revelation changed everything. If light existed beyond what we could see, what else might the universe contain that remained hidden from our senses? Understanding what light actually is took several more decades. James Clerk Maxwell, working in the 1860s, developed mathematical equations describing electricity and magnetism. These equations revealed that oscillating electric and magnetic fields could propagate through space as waves. When Maxwell calculated the speed of these electromagnetic waves, he found it matched the measured speed of light exactly. Light itself was electromagnetic radiation. More importantly, Maxwell's equations predicted that electromagnetic waves could exist at any frequency, not just the narrow band our eyes detect. This theoretical prediction needed experimental confirmation. Heinrich Hertz provided it in the 1880s by generating and detecting radio waves in his laboratory. The electromagnetic spectrum was real. An invisible universe of radiation existed at frequencies our eyes were never designed to perceive. The question became how to observe this invisible light and what it might reveal about the cosmos. Radio astronomy began almost by accident in the 1930s. Karl Jansky, an engineer investigating static interference in radio communications, built a rotating antenna to identify the source of the noise. After months of careful observation, he discovered that some of the interference came from the Milky Way itself. Our galaxy emitted radio waves. This discovery didn't immediately revolutionize astronomy. Most scientists focused on optical observations, believing radio waves wouldn't reveal much of interest. But a few pioneers recognized the potential, and after World War II, using surplus radar equipment, they began systematically mapping the radio sky. What they found transformed our understanding of the universe. The radio cosmos looked completely different from the visible one. The center of the Milky Way, obscured by dust clouds in optical light, blazed brightly in radio wavelengths. Distant galaxies that appeared unremarkable through telescopes emitted powerful radio signals. Supernova remnants glowed in radio light, revealing their structure and expansion. The universe spoke in radio waves, telling stories invisible to optical astronomy. Pulsars emerged from this radio exploration in 1967. Jocelyn Bell Burnell, analyzing radio telescope data, noticed strange regular pulses arriving with remarkable precision every 1.3 seconds. The regularity seemed almost artificial, leading to brief speculation about alien signals. But further observations revealed the truth. These pulses came from rapidly spinning neutron stars, the collapsed cores of massive stars that had exploded as supernovae. As these neutron stars rotate, beams of radio waves sweep across space like lighthouse beams. When Earth happens to lie in the path of the beam, we detect regular pulses. Neutron stars represent matter in its most extreme state, a mass greater than the Sun, compressed into a sphere only 20 kilometers across. A teaspoon of neutron star material would weigh billions of tons on Earth. The matter exists in forms impossible to create in any laboratory, governed by physics at the edge of our understanding. Yet through radio astronomy, we can study these objects in detail, even though we cannot see them with optical telescopes. Radio telescopes also revealed the large-scale structure of our galaxy. By mapping the radio emission from hydrogen gas throughout the Milky Way, astronomers traced the spiral arms, showing how our galaxy is organized. They discovered the supermassive black hole at the galactic center, invisible in optical light, but detectable through the radio emissions from hot gas swirling around it. Layer by layer, radio astronomy built a picture of our galaxy that visible light alone could never provide. Infrared astronomy developed more slowly because Earth's atmosphere absorbs most infrared radiation. Water vapor in the air blocks these wavelengths, making ground-based observations difficult. Astronomers built telescopes on high, dry mountains and carried instruments on balloons and aircraft to get above the moisture. But the real transformation came with space telescopes, rising above the atmosphere entirely. The infrared astronomical satellite, launched in 1983, mapped the entire sky in infrared wavelengths over 10 months. It discovered dust clouds where stars were forming, revealed the structure of the Milky Way obscured in visible light, and found entire galaxies that emit most of their light in the infrared. These observations showed that much of the action in the universe occurs hidden behind dust, visible only in wavelengths that can penetrate the obscuring material. Infrared observations reveal cool objects that barely shine in visible light. Brown dwarfs, failed stars too small to sustain nuclear fusion, emit primarily in infrared. The dusty disks around young stars where planets form glow warmly in these wavelengths. Even planets themselves, including those orbiting distant stars, can sometimes be detected in infrared, their faint heat signature distinguishable from their parent star's overwhelming glare. The Spitzer Space Telescope, operating from 2003 to 2020, spent nearly 2 decades observing the infrared universe. It peered inside stellar nurseries, watching stars being born in clouds of gas and dust. It characterized the atmospheres of planets orbiting other stars, detecting molecules like water vapor and methane. It discovered a massive, previously unknown ring around Saturn, invisible in ordinary light, but glowing faintly in infrared from the warmth of countless tiny impacts. Ultraviolet astronomy also required escaping Earth's atmosphere, which fortunately blocks these energetic photons that would otherwise harm life on the surface. Space-based ultraviolet telescopes revealed the hottest stars, those burning so intensely that most of their light emerges in ultraviolet wavelengths. They showed the violent environments around massive stars, where powerful winds and intense radiation sculpt surrounding gas into glowing nebulae. The Hubble Space Telescope, though famous for its visible light images, observes in ultraviolet and near-infrared as well. This multi-wavelength capability allows astronomers to study objects more completely. Hot young stars stand out in ultraviolet, while cooler old stars shine more brightly in infrared. By observing the same region in multiple wavelengths, scientists build a more complete understanding of what they're seeing. X-ray astronomy opened windows onto some of the most extreme processes in the universe. The first cosmic X-ray source beyond the Sun was discovered in 1962 during a brief rocket flight carrying X-ray detectors above the atmosphere. The source emitted thousands of times more X-ray energy than visible light. It turned out to be a neutron star, pulling matter from a companion star. The infalling material heats to millions of degrees before reaching the surface, glowing brilliantly in X-rays. Earth's atmosphere completely blocks X-rays, protecting life on the surface but requiring X-ray telescopes to operate in space. The Chandra X-ray Observatory, launched in 1999, has spent over 2 decades observing the X-ray universe. It images the hot gas in galaxy clusters, the expanding shock waves from supernova explosions, and the swirling material around black holes. These observations reveal processes occurring at temperatures and energies impossible to achieve on Earth. When massive stars explode, they leave behind expanding shells of debris heated to tens of millions of degrees. These supernova remnants shine brightly in X-rays. The Crab Nebula, remnant of a star that exploded in 1054, still glows intensely nearly 1,000 years later. At its center sits a pulsar, the collapsed core of the original star, spinning 30 times per second and pumping energy into the surrounding nebula. Galaxy clusters, the largest structures held together by gravity, contain most of their ordinary matter not in galaxies, but in hot gas filling the space between them. This gas, heated to tens of millions of degrees by gravitational compression, emits X-rays. Without X-ray observations, we would miss most of the ordinary matter in these enormous structures, thinking the galaxies themselves contained everything. Gamma-ray astronomy explores the highest energy phenomena in the universe. Gamma rays emerge from nuclear reactions, from particles accelerated to nearly the speed of light, and from matter falling into black holes. The Fermi Gamma-ray Space Telescope, launched in 2008, maps the gamma-ray sky continuously, revealing sources invisible in any other wavelength. Gamma-ray bursts, brief intense flashes lasting from milliseconds to several minutes, were discovered accidentally in the late 1960s by military satellites designed to detect nuclear weapons tests. For decades, their origin remained mysterious. Were they nearby objects or incredibly distant and therefore incredibly powerful? The answer came when astronomers began detecting the afterglows in optical and X-ray wavelengths. The bursts originated in distant galaxies, billions of light-years away. The energy released in a few seconds exceeded what the Sun will emit over its entire 10 billion-year lifetime. Long-duration gamma-ray bursts come from the collapse of massive stars. When a star much larger than the Sun exhausts its nuclear fuel, its core collapses to form a black hole. Some of the infalling material forms jets that drill through the star and shoot into space at nearly the speed of light, producing gamma rays through complex high-energy processes. Short-duration gamma-ray bursts come from the collision of two neutron stars, or a neutron star and a black hole. These mergers produce brief, intense gamma-ray flashes, along with other phenomena we can now detect. Each wavelength reveals different aspects of the same universe. Radio waves show cold gas and magnetic fields. Infrared reveals dust-shrouded processes and cool objects. Visible light displays stars and galaxies as our eyes would see them. Ultraviolet highlights hot stars and energetic regions. X-rays expose million-degree gas and compact objects. Gamma rays mark the most violent events and highest energy particles. Together, they construct a comprehensive picture far richer than any single wavelength could provide. But light in all its forms is just one way of perceiving the cosmos. Gravitational waves opened an entirely different channel of observation, unrelated to electromagnetic radiation. These are ripples in spacetime itself, predicted by Einstein in 1916 as a consequence of general relativity. If mass curves spacetime, then accelerating mass should produce waves in that curvature, propagating outward at the speed of light. Einstein himself doubted these waves could ever be detected. The effect would be incredibly weak, requiring extraordinarily sensitive instruments. For decades, gravitational waves remained a theoretical curiosity. In the 1970s, observations of a binary pulsar system provided indirect evidence. Two neutron stars orbiting each other were gradually spiraling closer together, losing energy exactly as predicted if they were radiating gravitational waves. But detecting the waves directly required even more sophisticated technology. The Laser Interferometer, Gravitational Wave Observatory, consists of two facilities with 4-kilometer-long arms arranged in an L shape. Powerful lasers travel down these arms, bounce off mirrors, and recombine. When a gravitational wave passes through, it stretches space in one direction while compressing it perpendicular to that direction. This changes the lengths of the arms by an incredibly tiny amount, far less than the width of a proton. On September 14, 2015, both detectors registered a signal. The characteristic pattern showed two massive objects spiraling together and merging. Analysis revealed two black holes, one 36 times the Sun's mass and the other 29 times the Sun's mass, colliding 1.3 billion light-years away. In a fraction of a second, 3 times the Sun's mass converted entirely into gravitational wave energy. For that brief moment, this collision released more power in gravitational waves than all the stars in the observable universe combined produce in light. This detection opened gravitational wave astronomy. Since then, dozens of black hole mergers and several neutron star collisions have been detected. Each event provides information about the masses and properties of the merging objects and tests general relativity in conditions impossible to probe any other way. In 2017, a neutron star merger was observed in both gravitational waves and electromagnetic radiation across the spectrum. This multi-messenger observation, combining gravitational waves with light, neutrinos, and other signals, provided insights neither could deliver alone. Neutrino astronomy offers yet another window. Neutrinos barely interact with matter, allowing them to escape from regions too dense for light to penetrate. The first neutrino detector designed for astronomy was built in the late 1960s. A large tank of cleaning fluid sat deep in a gold mine, shielded from cosmic rays. Occasionally, a neutrino from the Sun would interact with a chlorine atom in the fluid, converting it to radioactive argon. Over months, just a few dozen argon atoms accumulated, clear evidence of solar neutrinos reaching Earth. The detector found only about 1/3 as many neutrinos as models predicted. This solar neutrino problem puzzled physicists for decades. The solution involved fundamental particle physics. Neutrinos come in 3 types, and they oscillate between these types as they travel. The detector only captured one type, missing the others that had transformed during their journey from the Sun's core. When a massive star exploded, as supernova 1987A in a nearby galaxy, neutrino detectors on Earth registered a burst of about 24 neutrinos over 13 seconds. These particles escaped the collapsing core hours before the shock wave reached the surface and the star began brightening in visible light. This confirmed theoretical models of supernovae and marked the first detection of neutrinos from beyond our solar system. Modern neutrino detectors are enormous. IceCube uses a cubic kilometer of Antarctic ice as its detector. When a very high-energy neutrino interacts in the ice, it produces particles that emit faint flashes of light. Arrays of sensors frozen deep in the ice register these flashes, allowing reconstruction of the neutrino's energy and direction. IceCube has detected neutrinos from distant galaxies, cosmic neutrinos, produced by the most energetic processes in the universe. The cosmic microwave background deserves special attention. This is the oldest light in the universe, released when the cosmos was only 380,000 years old. Before that time, the universe was so hot and dense that matter existed as ionized plasma. Photons constantly scattered off free electrons, making space opaque. As the universe expanded and cooled, electrons and protons combined to form neutral hydrogen. Suddenly, photons could travel freely. The light released at that moment has been traveling through space ever since, stretched by cosmic expansion from visible wavelengths into microwaves. This radiation was predicted in the late 1940s as a consequence of the Big Bang theory. If the universe began hot and dense, it should be filled with cool radiation left over from that early state. In 1964, 2 radio astronomers discovered this background radiation accidentally while testing an antenna. They found persistent noise coming equally from all directions, corresponding to a temperature about 3 degrees above absolute zero. This discovery confirmed the Big Bang theory and provided evidence for the universe's history. The cosmic microwave background is remarkably uniform, having almost the same temperature in every direction, but not perfectly uniform. Tiny fluctuations, differences of only 1 part in 100,000, reveal density variations in the early universe. These slight differences were the seeds from which all structure grew. Satellites have mapped these fluctuations with increasing precision. The pattern of slightly hotter and cooler regions encodes information about the universe's age, composition, geometry, and evolution. This invisible microwave glow, undetectable by human senses, contains the history of everything written in subtle temperature variations. Dark matter reveals itself only through gravity. It doesn't emit, absorb, or reflect light. It doesn't produce detectable neutrinos or gravitational waves, yet we know it exists through its gravitational influence. The first evidence came in the 1930s from studying galaxy clusters. Galaxies within clusters move too fast. The visible matter provides only about 1% of the gravity needed to hold them together. Something invisible supplies the rest. In the 1970s, measurements of how spiral galaxies rotate revealed similar problems. Stars in the outer regions orbit at the same speed as stars closer to the center, contrary to predictions based on visible matter. Either gravity works differently on large scales, or invisible matter extends far beyond the visible disk. Gravitational lensing provided more evidence. Mass bends light, so when light from distant galaxies passes near a massive galaxy cluster, the cluster's gravity acts like a lens, distorting background images. By measuring this distortion, astronomers map the mass distribution, both visible and invisible. These maps consistently show that most mass is dark matter, distributed in vast halos around and between galaxies. Computer simulations of structure formation only reproduce observed galaxy distributions if dark matter is included. Without it, simulations fail to match reality. With it, they produce structures remarkably similar to observations. Dark matter provided the gravitational scaffolding within which galaxies formed and evolved. Many experiments search for dark matter particles directly. Deep underground, shielded from cosmic rays, sensitive detectors wait for a dark matter particle to collide with an atomic nucleus. So far, no confirmed detections exist, placing constraints on possibilities, but not yet identifying what dark matter is. We know it exists. We know approximately how much there is. We know it shaped cosmic structure, but we don't know what it's made of. Dark energy is even more mysterious. The discovery came from observations of distant supernovae in the late 1990s. A particular type of supernova has consistent peak brightness, allowing astronomers to calculate distance by measuring how bright it appears. Two teams independently measured distances and velocities of dozens of distant supernovae, expecting to find the expansion slowing due to gravity. Instead, they found acceleration. Distant supernovae were fainter than expected, farther away than expected, meaning expansion was speeding up. Something was pushing space apart, overwhelming gravity. This mysterious influence became known as dark energy. It comprises about 68% of the universe's total energy. Unlike matter, which becomes less dense as space expands, dark energy maintains constant density. As the universe expands, more space exists, containing more dark energy, causing faster expansion. This creates a feedback loop that will ultimately determine the universe's fate. The simplest explanation is the cosmological constant, energy intrinsic to space itself. Every cubic centimeter of empty space contains a tiny amount of vacuum energy. This doesn't diminish with expansion because it's a property of space rather than something within space. The value required to explain observations is incredibly small, yet precisely what we measure. Why it has this particular value remains unexplained. Through all these methods, from radio telescopes to gravitational wave detectors to neutrino observatories, humanity has extended perception far beyond what evolution provided. Each technique reveals aspects of the universe invisible to the others. Together, they construct a picture of reality far richer and stranger than our eyes alone could ever show. The invisible universe isn't separate from the visible one. It's the same cosmos, simply operating in wavelengths and through forces our biological senses cannot detect. What appears as darkness to our eyes blazes in radio waves. What seems empty contains dark matter and dark energy. What looks static ripples with gravitational waves. Space itself, seemingly empty and passive, curves under mass and carries intrinsic energy. We've learned that perception is limited but extensible. Our eyes show us a thin slice of reality, but our minds can conceive instruments to detect what our senses miss. The invisible becomes visible through technology and understanding. Mysteries remain, certainly. Dark matter and dark energy are known to exist but not understood. The nature of quantum reality continues to puzzle. The ultimate fate of the universe remains uncertain. Yet each question answered reveals the universe to be knowable, following natural laws we can discover and comprehend. The cosmos doesn't hide deliberately. It simply exists in forms our senses weren't designed to perceive. Through patience and ingenuity, we extend our awareness into these hidden realms, making the invisible visible, the unknown known, piece by piece, discovery by discovery. Building understanding that spans from the quantum foam to the cosmic web, from the first moments after the Big Bang to the accelerating expansion that will shape all future ages. The fabric of invisible reality. We've explored what lies beyond human sight and how we learn to perceive it. Now we turn to something deeper, the fundamental nature of this invisible reality and what it tells us about existence itself. The universe operates according to principles that remain hidden from casual observation, yet reveal themselves through careful study and patient contemplation. Space and time form the stage upon which everything occurs, yet these aren't the simple, absolute entities they appear to be. Einstein's theories of relativity transformed our understanding of space-time itself, revealing it to be dynamic, flexible, and intimately connected to matter and energy. This invisible fabric underlies all of reality, bending and flowing in ways our everyday experience never hints at. Imagine space-time as a flexible sheet. Place a massive object on it, and the sheet curves, creating a depression. Other objects moving nearby follow the curves in the sheet, which we perceive as gravitational attraction. This isn't just a metaphor. Mass genuinely curves space-time, and objects genuinely follow the straightest possible paths through that curved geometry. What we call gravity is actually the geometry of space-time itself. This curvature affects not just space, but time as well. Clocks run slower in stronger gravitational fields. Near a black hole's event horizon, time dilation becomes extreme. From a distant observer's perspective, time appears to stop for anything approaching the horizon. Yet for the falling object, time continues normally. The universe doesn't have a single universal time that flows the same everywhere. Time itself is local, relative, dependent on motion and gravity. These effects, while dramatic near black holes, exist everywhere in smaller amounts. GPS satellites orbit high above Earth, where gravity is slightly weaker. Time passes fractionally faster there than on the surface. The difference amounts to only microseconds per day, but GPS systems must account for this relativistic time dilation to provide accurate positions. The The technology in your pocket relies on understanding invisible properties of spacetime. Light traveling through curved spacetime follows curved paths. When light from a distant galaxy passes near a massive galaxy cluster, the cluster's gravity bends the light's path, acting as a gravitational lens. Sometimes this creates multiple images of the same background galaxy, distorted into arcs or rings around the foreground cluster. These lensing effects allow astronomers to map dark matter distributions and study objects too distant to see otherwise. The strongest gravitational lensing occurs near black holes. Light passing close to a black hole's event horizon bends dramatically. Some light orbits the black hole multiple times before escaping. This creates complex patterns of distortion and magnification. In 2019, the Event Horizon Telescope captured an image of the supermassive black hole at the center of the galaxy M87. The image shows a bright ring of light surrounding a dark central region. The ring is light from hot gas orbiting the black hole, bent and amplified by the black hole's intense gravity. The dark center is the black hole's shadow, the region from which no light can escape. Black holes represent the ultimate invisible objects. They emit no light, produce no radiation we can directly detect, yet they profoundly affect their surroundings. Gas falling toward a black hole heats through friction and compression, glowing brilliantly before crossing the event horizon. Jets of material sometimes shoot away from the vicinity of black holes at nearly the speed of light, powered by magnetic fields and the rotational energy of the black hole itself. At the center of most large galaxies sits a supermassive black hole, millions or billions of times the Sun's mass. Our own Milky Way contains one roughly 4 million solar masses, located 26,000 light-years from Earth. Stars orbit this invisible monster, their motions revealing its presence and properties. The closest stars complete orbits in just a few years, moving at thousands of kilometers per second. Only an incredibly massive compact object could produce such extreme orbital velocities. These supermassive black holes played a crucial role in galaxy formation and evolution. As gas falls toward them, the released energy can heat and expel gas from the galaxy, regulating star formation. Galaxies and their central black holes appear to grow together, maintaining a consistent relationship between black hole mass and galaxy properties. The invisible black hole at a galaxy's heart influences the entire visible structure surrounding it. Quantum mechanics governs reality at the smallest scales, introducing invisibility of a different kind. At quantum scales, particles don't have definite positions or velocities until measured. They exist in superpositions, being in multiple states simultaneously. A particle can be in multiple places at once, following multiple paths, existing in a blur of probability that only collapses into a single definite state when observed. This isn't because our instruments disturb the system. It's the fundamental nature of quantum reality. Particles are inherently uncertain, fundamentally probabilistic. The famous double-slit experiment demonstrates this beautifully. Send individual particles through two slits, and they create an interference pattern on a screen behind the slits, as if each particle passes through both slits simultaneously and interferes with itself. Yet if you measure which slit the particle passes through, the interference pattern disappears. The act of observation changes what happens. Wave-particle duality means quantum objects behave as both waves and particles depending on how you observe them. An electron is neither purely a particle nor purely a wave. It's something that exhibits properties of both under different circumstances. This duality extends to all quantum objects, including photons of light. Light behaves as a wave when diffracting around obstacles or interfering with itself. It behaves as particles when interacting with matter, transferring energy in discrete packets. Quantum entanglement creates connections between particles that persist regardless of distance. When two particles become entangled, measuring a property of one instantly affects the other, even if they're separated by vast distances. This doesn't transmit information faster than light, but it does create correlations that seem to transcend space itself. Einstein called this spooky action at a distance, uncomfortable with its implications. Yet experiments have repeatedly confirmed that entanglement is real. These quantum effects remain invisible to direct perception. You cannot see superposition or observe wave-particle duality with your eyes. Quantum mechanics operates at scales far too small and in ways too strange for everyday intuition. Yet it's absolutely real, confirmed by countless experiments and embodied in the technology we use daily. Computers, lasers, solar panels, LED lights all depend on quantum mechanics being correct. The quantum vacuum itself is not truly empty. Even with no particles present, quantum fields permeate all space. These fields fluctuate constantly, with virtual particles appearing and disappearing in fleeting moments. These quantum fluctuations are real and measurable. They affect the energy levels of atoms. They produce a subtle force between nearby metal plates in vacuum, the Casimir effect, which has been precisely measured. This quantum vacuum energy may be related to dark energy, the mysterious influence causing cosmic expansion to accelerate. If the vacuum has intrinsic energy, that energy would behave exactly like dark energy, maintaining constant density as space expands. However, calculations of vacuum energy based on quantum field theory predict a value enormously larger than observed, 120 orders of magnitude larger. This discrepancy represents one of the deepest unsolved problems in physics. Fields are fundamental to modern physics. Electric and magnetic fields, the electromagnetic field, the fields associated with nuclear forces, even particles themselves are understood as excitations in quantum fields. An electron is not a tiny ball, but an excitation in the electron field that permeates all space. A photon is an excitation in the electromagnetic field. The universe consists of overlapping fields filling all space, with particles representing local concentrations of energy in these fields. These fields are invisible. You cannot see or touch an electromagnetic field directly. You perceive only its effects when it interacts with matter. Yet the field exists everywhere, carrying information about electric charges and magnets, transmitting light across empty space. Understanding reality through fields rather than objects represents a profound shift in how we conceptualize existence. The Higgs field permeates all space, giving mass to fundamental particles through their interactions with it. Particles that interact strongly with the Higgs field have large masses. Those that don't interact remain massless. The photon doesn't interact with the Higgs field, which is why light has no mass and travels at the speed of light. Electrons and quarks do interact, which is why they have mass and cannot reach light speed. The Higgs boson, discovered at CERN in 2012, is an excitation in the Higgs field. Its detection confirmed that the Higgs field exists and operates as theorized. This invisible field filling all space determines one of the most fundamental properties of matter, its mass. Without the Higgs field, particles would be massless and atoms could not form. Matter as we know it would not exist. Dark matter likely consists of particles that barely interact with ordinary matter, passing through it like ghosts. These particles would be affected by gravity and possibly by weak nuclear forces, but not by electromagnetism. They wouldn't emit, absorb, or scatter light. They would be invisible not just to our eyes, but to all electromagnetic observations. Enormous efforts are underway to detect these particles directly, using increasingly sensitive detectors in deep underground laboratories, shielded from cosmic rays and other background radiation. Some theories suggest dark matter particles occasionally collide and annihilate, producing gamma rays or other particles we could detect. Satellites and ground-based telescopes search for these signals from regions where dark matter should be concentrated, like the center of our galaxy. So far, no conclusive detections have been made, but the search continues, narrowing the possibilities for what dark matter could be. The structure of the universe at the largest scales formed under the influence of dark matter. In the early universe, slight density fluctuations existed, regions with slightly more or less matter than average. Gravity amplified these differences. Regions with more matter attracted even more matter, while regions with less lost material to denser areas. Over hundreds of millions of years, this process created the cosmic web, a network of filaments connecting galaxy clusters with vast voids in between. Simulations of this process show that ordinary matter alone cannot produce the observed structure. The cosmic web forms too slowly without dark matter. But when simulations include dark matter, providing 5 times as much gravitational influence as ordinary matter, the structures that form match observations beautifully. The invisible dark matter scaffolding guided the distribution of visible matter into the patterns we observe today. The cosmic web extends across billions of light-years, too vast for any direct observation. We know its structure by mapping the positions of millions of galaxies, building a 3-dimensional picture of the universe's large-scale organization. Galaxies trace the filaments, clustering where dark matter is densest. The voids between filaments are not completely empty, but contain far fewer galaxies than the filaments themselves. Within this cosmic web, galaxies evolve over billions of years. They form from collapsing gas clouds, grow through star formation and mergers with other galaxies, and eventually exhaust their gas supplies and fade as their stars age. The Hubble Space Telescope has observed galaxies at various distances and therefore various times in the past, creating a visual timeline of galaxy evolution. Early galaxies appear small, irregular, and actively forming stars. Modern galaxies are larger, more organized, with many having exhausted their star-forming gas. Our Milky Way galaxy appears as a flat disk when viewed from within, but extensive mapping reveals its true 3-dimensional structure. The disk contains most of the visible stars, gas, and dust, organized into spiral arms. Above and below the disk extends a spherical halo containing old stars and globular clusters, and surrounding everything is the dark matter halo, extending far beyond the visible parts, providing the gravity that holds the galaxy together. The Milky Way is not isolated. It belongs to the Local Group, a collection of about 50 galaxies spanning several million light-years. The largest members are the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. The rest are smaller dwarf galaxies, many of which orbit the Milky Way like satellites. The Local Group is bound by gravity, with Andromeda and the Milky Way slowly approaching each other. In about 4 billion years, they will collide and merge, forming a larger elliptical galaxy. This merger will be dramatic but not catastrophic. Stars are so widely spaced that direct collisions between them will be extremely rare. The galaxies will pass through each other, with gravity distorting their shapes, pulling out tidal tails of stars. Gas clouds will collide, triggering bursts of star formation. The supermassive black holes at the centers of both galaxies will eventually merge into a single larger black hole. Over hundreds of millions of years, the merged system will settle into a new configuration, and star formation will gradually cease as gas is consumed or expelled. Time scales in astronomy often exceed human comprehension. Processes we describe casually take millions or billions of years to unfold. Stars form over millions of years. They live for millions or billions of years depending on their mass. They die in various ways, sometimes gradually, sometimes explosively, but always on timescales vast compared to human lifetimes. Galaxies evolve over billions of years. The universe itself is 13.8 billion years old, an almost incomprehensible span. Yet we can observe these processes because we see objects at different stages of their lives. By observing many stars of different ages, we understand stellar evolution. By observing galaxies at various distances, and therefore various times in the past, we understand how galaxies form and change. The universe is so large that light takes billions of years to cross it, which means looking at distant objects is looking backward in time. The most distant objects we observe are seen as they were when the universe was young. Light from these galaxies has been traveling for over 13 billion years to reach us. We see them as they were in the early universe, small, irregular, forming stars rapidly. Closer galaxies, seen as they were more recently, show more mature structures. Nearby galaxies show current structures and properties. This ability to observe different cosmic epochs by looking at different distances allows astronomers to reconstruct the universe's history. The cosmic microwave background radiation provides a snapshot of the universe at age 380,000 years, when it first became transparent. The slight temperature fluctuations in this radiation reveal density variations that later grew into galaxies and clusters. By analyzing these fluctuations in detail, cosmologists can determine fundamental properties of the universe with remarkable precision. The universe is flat, meaning parallel lines remain parallel as they extend indefinitely. The total energy density equals the critical density needed for flatness. This total includes ordinary matter, dark matter, and dark energy in proportions we can now measure accurately. Ordinary matter comprises about 5%, dark matter about 27%, dark energy about 68%. These values are known to within a few percent uncertainty, a remarkable achievement given that most of the universe consists of things we don't directly detect or understand. The universe is also homogeneous and isotropic on large scales, meaning it looks the same in all directions and has the same properties everywhere. This uniformity emerged from quantum fluctuations in the earliest moments after the Big Bang, amplified by a brief period of exponential expansion called inflation. Inflation stretched tiny quantum fluctuations to cosmic scales, seeding the structure we observe today. Inflation theory predicts specific patterns in the cosmic microwave background fluctuations, patterns that have been confirmed by observations. It explains why the universe is so uniform, why it's flat, and where structure came from. Yet inflation itself raises questions. What caused it? What is the inflaton field that drove it? Did it occur just once, or does it continue in other regions beyond our observable universe, creating a vast multiverse of separate regions with potentially different properties? These questions remain open, perhaps forever unanswerable, if the other regions are truly beyond observation. We may live in one bubble within an infinite multiverse, unable to observe or test what lies beyond our cosmic horizon. Or we may live in a finite, unique universe. Current observations cannot distinguish between these possibilities. The accelerating expansion driven by dark energy determines the universe's ultimate fate. As expansion accelerates, galaxies beyond our local group will eventually recede faster than light can travel through the expanding space between us. They will disappear beyond our cosmic horizon, becoming forever unreachable. Billions of years in the future, only the merged remnant of the Milky Way and Andromeda and a few nearby dwarf galaxies will remain visible. The rest of the universe will have expanded beyond observability. Stars will continue forming for tens of billions of years, but the gas supply is finite. Eventually, star formation will cease. Existing stars will age and die. Small stars like the Sun will become white dwarfs, slowly cooling over trillions of years. Massive stars will explode and leave behind neutron stars or black holes. Over time, scales almost beyond imagining, even the longest-lived stars will fade and die. In the far future, trillions of years from now, the universe will be dark and cold. Galaxies will consist of dead stellar remnants, white dwarfs, neutron stars, and black holes. Even these objects will eventually decay through processes so slow they might take 10 to the 100 years or longer. Black holes themselves will gradually evaporate through Hawking radiation, an incredibly slow process where quantum effects near the event horizon cause them to lose mass over time. The largest black holes will take 10 to the 100 years to evaporate completely. In this ultimate fate, the universe approaches a state of maximum entropy, with energy distributed as uniformly as possible. No stars shine, no structures remain. Only a thin soup of photons and perhaps some exotic particles, all at nearly zero temperature, separated by vast expanding distances. This heat death represents the final state toward which the second law of thermodynamics drives all closed systems. Yet even these predictions assume our current understanding is correct. We don't know what dark energy truly is. If it's more than a simple cosmological constant, if it changes over time, the universe's fate could be different. If dark energy strengthens, it could eventually tear apart galaxies, then solar systems, then planets, then atoms themselves in a big rip. If dark energy weakens or reverses, expansion could slow and eventually reverse, leading to a big crunch where everything collapses back together. Current observations suggest dark energy is consistent with being a cosmological constant, unchanging over time. But observations span only a fraction of cosmic history. We cannot be certain dark energy will remain constant forever. The universe has surprised us before and may surprise us again. What we can say with confidence is that the universe operates according to natural laws, laws we've discovered through observation and experiment. These laws govern both the visible and invisible aspects of reality. Electromagnetism, gravity, the strong and weak nuclear forces, quantum mechanics, thermodynamics, all these principles operate consistently, making the universe comprehensible and predictable. The invisible universe is not mysterious in the sense of being unknowable. It's mysterious only in that we don't yet understand all of it. Each mystery solved reveals deeper mysteries, but also confirms that the universe is knowable, that patient investigation reveals truth. Dark matter and dark energy are real phenomena with real effects. We will eventually understand what they are, even if that understanding takes decades or centuries more effort. The tools we've developed to perceive the invisible universe represent humanity's greatest intellectual achievements. From telescopes to particle accelerators to gravitational wave detectors, each instrument extends perception into realms evolution never prepared us for. Yet more remarkably, we've developed the mathematics and conceptual frameworks to understand what we observe. Maxwell's equations, Einstein's relativity, quantum mechanics, the standard model of particle physics. These theories make accurate predictions about phenomena far removed from everyday experience. Science works through a cycle of observation, hypothesis, prediction, and testing. When predictions match observations, confidence in the theory grows. When they don't, theories must be revised or replaced. This process gradually builds understanding, correcting errors, refining models, approaching closer to truth. It requires humility to accept when theories are wrong and creativity to imagine alternatives. The invisible universe surrounds us always. We move through invisible fields, carried along by space-time curvature, embedded in dark matter halos, surrounded by neutrinos and cosmic rays and gravitational waves. Most of reality operates beyond our senses, yet it's all part of the same unified physical system. The visible and invisible aren't separate realms, but different aspects of one cosmos. Understanding this should inspire both humility and wonder. Humility because our natural perception shows us so little of what exists. Wonder because through thought and creativity, we've learned to perceive what our senses cannot detect. The universe is stranger and more beautiful than it appears, filled with phenomena invisible to the eye but visible to the mind. As we conclude this exploration, consider what we've discovered. The electromagnetic spectrum extends far beyond visible light, with most wavelengths invisible to human eyes. Dark matter comprises most of the matter in the universe, detectable only through gravity. Dark energy drives accelerating expansion, though we don't understand what it is. Spacetime is curved, dynamic, relative. Quantum mechanics governs small scales with probabilistic uncertainty. Fields permeate all space. Time is not absolute. Nothing can travel faster than light. The universe began in a hot, dense state and has been expanding and evolving for nearly 14 billion years. All of this knowledge came from observing what we cannot see, from building instruments to extend perception, from developing mathematical frameworks to describe invisible phenomena. Humans, limited biological creatures confined to one planet, have nonetheless learned to comprehend a universe that extends billions of light years and operates according to principles that defy everyday intuition. This is not the end of discovery, but a milestone along an ongoing journey. Many mysteries remain. What is dark matter? What is dark energy? How do quantum mechanics and gravity unify? What happened in the first moments after the Big Bang? Are there dimensions beyond the three spatial dimensions and one time dimension we perceive? Is our universe unique or part of a larger multiverse? These questions await answers. Future instruments will probe deeper. Future theories will explain more. The universe will continue revealing itself to those who observe carefully and think creatively. The invisible will become visible. The unknown will become known. Understanding will deepen. What remains constant is that the universe is knowable. Reality follows natural laws that operate consistently. Observation and reason can reveal truth. The cosmos doesn't hide deliberately, but simply exists in forms our senses didn't evolve to perceive. Through science and technology, we overcome these limitations, extending awareness into hidden realms, making the invisible visible. The universe beyond human sight is vast, strange, and beautiful. It includes most of what exists, operating in wavelengths we cannot see, through forces we cannot feel, in particles we cannot detect directly. Yet it's not beyond understanding. Patient investigation reveals its nature. Mathematics describes its behavior. Instruments extend our senses to perceive it. You live in this invisible universe. It surrounds you, permeates you, affects you constantly. Neutrinos pass through your body by the billions each second. Gravitational waves ripple through your position. Dark matter fills the space around you. Quantum fields fluctuate throughout every point of space. The electromagnetic spectrum bathes you in invisible radiation, from radio to gamma rays. Space-time curves under Earth's mass, affecting how time passes for you compared to someone at higher altitude. None of this is perceptible to your senses, yet all of it is real. The invisible universe is not separate from the visible one you perceive. They're the same reality, the same cosmos, simply experienced at different levels. Understanding this deepens appreciation for existence itself, for the remarkable fact that the universe exists at all, and that it contains beings capable of understanding it. Take comfort in knowing that reality is knowable even when invisible. Mystery is not the same as unknowability. What seems hidden can be revealed through careful study. The universe rewards curiosity with understanding, patience with knowledge, observation with insight. What we cannot see, we can still comprehend. What we cannot touch, we can still understand. What appears invisible becomes visible through human creativity and persistence. Rest with these thoughts. The universe extends far beyond what your eyes can show you, but your mind can grasp what your senses cannot detect. The invisible universe is real, vast, and ultimately comprehensible. Through science, we make the unseeable seen, the unknowable known, building understanding piece by piece across generations. This journey of discovery continues, always revealing more, always opening deeper questions, always showing that reality is richer and stranger than we imagined, yet ultimately knowable to minds willing to observe, question, and think carefully about the nature of existence. The universe reveals itself not through miracles or mysticism, but through natural laws operating consistently across all scales of space and time. Every phenomenon we've explored, from gravitational waves to dark energy, from quantum superposition to cosmic structure, follows mathematical principles that can be discovered through observation and reason. What makes this remarkable is not that the universe is comprehensible, but that beings like us, evolved on one small planet, possess the capacity to comprehend it. Our brains developed to navigate immediate survival challenges, yet they can grasp concepts like curved spacetime and quantum fields. This suggests something profound about the relationship between mind and cosmos. The invisible universe teaches us that perception is limited, but understanding is not. We cannot see radio waves or dark matter or gravitational waves, yet we know they exist because we observe their effects and develop theories that make testable predictions. When predictions match observations, confidence grows. When they don't, theories adapt. This process, repeated across centuries, builds reliable knowledge about reality. Science does not claim absolute certainty. Dark matter and dark energy remain mysterious, not because they're unknowable, but because we haven't yet gathered sufficient data to determine their nature definitively. This humility before the unknown, combined with confidence that investigation can reveal truth, characterizes the scientific approach. We know what we know, acknowledge what we don't, and continue investigating. The universe is not designed for human convenience. Most of reality operates beyond our senses, in wavelengths we cannot see, through forces we cannot feel, at scales both vastly larger and incomprehensibly smaller than our everyday experience. Yet none of this makes the universe hostile or indifferent to understanding. It simply exists following its laws, regardless of whether anyone observes or comprehends it. What we call the invisible universe is simply the universe, most of which happens to be invisible to human eyes. There is no fundamental divide between seen and unseen. All of reality is part of one unified physical system, operating according to the same underlying principles. The visible portion is not separate from or more real than the invisible portions. They're all equally real, all equally part of existence. This knowledge should inspire neither fear nor existential despair, but rather a sense of profound wonder. We live in a cosmos vastly larger and stranger than our ancestors imagined, yet we've developed the tools and concepts to explore it. The universe rewards curiosity with understanding. Each mystery solved reveals deeper mysteries, ensuring the journey of discovery never ends. Ultimately, the invisible universe reminds us that reality is not limited to what we can directly perceive. Human experience, while valid and important, represents only a tiny fraction of what exists. Most of the cosmos operates beyond our awareness, yet it's all part of the same magnificent reality we inhabit. Understanding this doesn't diminish human significance, but rather places it in proper context as one remarkable phenomenon among countless others in a universe that has been unfolding for nearly 14 billion years and will continue for trillions more. The universe beyond human sight is not an absence but a presence, not emptiness but fullness, not mystery in the sense of being unknowable, but mystery in the sense of not yet fully understood. And that is perhaps the most hopeful conclusion of all, that the universe is knowable, that reality follows natural laws, that patient investigation reveals truth, and that the journey of discovery continues as long as curious minds persist in asking questions and carefully observing the cosmos that contains us all.